Let me first say hi to everyone and good morning to all. I know that you have been listening for last 4 days, but given this environment which I saw today morning going around, I think it's a pleasant environment and you must be energized again for the day today. Well, before I start, let me quickly ask how many of you have at least studied the basic fundamentals of fluid mechanics? I could say many hands or almost all hands raised. So that makes my life or job easy. So I will not then go in depth into the fundamentals of fluid mechanics that you already know, but I'll just try to give a quick catch up of the basic things that we have studied. Then I'm going to look at the applications of fluid mechanics in ocean engineering and ocean science to say, and that will possibly give you the perspective of various basic fundamentals that we have studied, how we can take it to the applications and ocean engineering and ocean science. If there is some doubt at some point of time, please interrupt me at that point. Don't hesitate. Don't keep it to the end. Well, now going to fluid mechanics, I'll rush through the first couple of slides because we know already what is fluid mechanics, or basically, first of all, if I say what is fluid, this explains what is fluid. Okay, so all your substance that you can define or differentiate between solid, gas, and fluid, right? So the state of the material you can define. I will not get into that. A substance in liquid or gas phase is referred to as fluid. Okay. Now let us come to mechanics. It is simple. When you apply some force, then what happens? You try to understand the behavior of the stationary or moving bodies that are subjected to the forces. And when it is applied to the fluids, you call it fluid mechanics. Very simple. So now, fluid mechanics we study in rest or in motion. So when we try to understand the fluid mechanics at rest, we call it fluid statics. Then we have something called fluid kinematics and fluid dynamics. So just to quickly differentiate between these three, fluid statics, fluid at rest, you try to understand. Fluid kinematics, you try to understand the fluid motion without considering the forces and energy involved in it. Then fluid dynamics, you do consider the forces. Okay. So now let me quickly move. This is the very basic expression we all have possibly seen. We try to find out the pressure under a fluid or within the fluid. P, that is equals to what? Gamma multiplied by H. It's the basically height of fluid that is standing over the reference plane that you are looking at. And gamma is nothing but your unit weight of that fluid. So applications, there are many. You try to find out the atmospheric pressure and you try to find out the gauge pressure or local pressure or anything that we do. There are a lot of applications of that. Then quickly, we have other applications. We talk about streamlines. You take various bodies, whether it is aerodynamics or hydrodynamics, anything you take, you talk about basically the streamlining of the body surface so that the resistance is going to less. I'm not going to talk about the drag that is going to act on the body, that skin friction drag, pressure drag. I will not cover all that. But there are applications of these basic fundamental concepts. We also have applications in dams and all that we deal with. You have also some places where you deal with the, basically you can talk about path line, but we also talk about that when we talk in terms of the particle motions or Lagrangian motion of various particles in the fluid. And we try to apply that in various ways. This is one example that is shown here for oil spill propagation in the sea or in the ocean. But there are a lot of applications. You talk about pollution and you want to find out where these pollutants are coming from. You go by backtracking. So you apply Lagrangian techniques. So in addition, there is a parallel technique in fluid mechanics or fluid dynamics that's called Eulerian technique. So the basic difference, can anyone explain what is the difference between Eulerian and Lagrangian techniques? Yeah.
Earlier technique, the sensor is at static position. In Lagrangian, it's moving with the flow. So that's why in Lagrangian, for example, radius only is the Lagrangian part, and in Eulerian, a sensor that's attached to a pole. That is
right. So basically, if I just rephrase what he said, is if you have a specific reference frame and you try to analyze your flow within that reference frame over a period of time, then you call it Eulerian frame of reference. But if you try to move along with the particle or mass or the element that you have considered and try to understand how this particle dynamics or the behavior changes with the flow, then you call it Lagrangian frame of reference. It's simple. You are sitting inside your house looking at the window and watching, let's say in the river, there is some flow going. So your reference frame is fixed and you are just watching the flow that is happening through that window. Now you are sitting in a boat in the same river. Now you are watching the flow that is happening around the boat. You are moving along with that mass of water or mass of fluid. So it is in the Lagrangian frame of reference. So these two basic differences we deal with. Now, what is that basic governing equation that we use to solve all these problems? Most of the times we have these equations which will come into picture. One set is continuity equation, the next set is momentum equations. And all together we call them in fluid mechanics Navier-Stokes equations. Okay. So there are different terms. You have convective terms, you have temporal or local acceleration, then you have the gravitational or the body force, then you have the pressure force, then viscous force. Okay. So this is very simple expression which we have studied in Newton's second law. What is that? F is equals to mass into acceleration. So on the right side you have force, and this is what? Acceleration. Where is the mass? The whole expression is per unit mass. Okay, that's what we do. All right. Now let me quickly move because fundamentals you already have studied. So most of the times we go for two types of solutions: exact solutions or approximate solutions for these expressions or the mathematical equations. Exact solutions, there are only few, which is applicable only for some standardized problem statements. But most of the cases we go for approximate solutions. And in approximate solutions, we have again two classifications. One set, we know that there is viscous forces are very large compared to inertia force. So there is there are solutions like you have Stokes law that you derive, that is based on where the viscous force is going to be very large, very large compared to inertia force. And the second set is viscous force are quite small relative to inertia force. Okay, so how do we differentiate? Is there any specific parameter which can actually indicate us to differentiate between these two types of problems? Reynolds number. What is Reynolds number? Anyone? Is the ratio between inertia to viscous force, right? Inertia force to viscous force. So RE, Reynolds number, you put it rho VD by nu, all that you do, right? So now, if your Reynolds number is very, very less than 1 or so, then you call viscous force is quite strong. But if it is, let us say, 1,000, 10,000, 100,000 and so on, then the inertia force is higher or larger. So now when the inertia force is larger, we basically deal with the boundary layer theories. And there we talk about the laminar boundary layer, transitional layer, turbulent layer and all that. But boundary layer is a very, very complicated subject to understand, but interesting subject as well. And application wise, it has quite large applications because practical scenarios, most of the fluid flow problems are high Reynolds number flows. So you deal with the boundary layer. And in atmospheric science and oceanic science, we talk about various processes and phenomena. So there we deal with boundary layer. Now, if we talk about ocean atmospheric interaction, so we obviously deal with the boundary layer. And any transfer of flux that happens from atmosphere to ocean or ocean to atmosphere, that happens through the boundary. So the boundary layer plays a major role. So understanding this boundary layer theory is very, very important. But anyway, I will not go and explain the boundary layer theory as such right now, but just wanted to place the importance of that. So these are the various drags and all that we deal with the boundary layer. Again, you talk about airfoils, the variation of pressure distribution and the leap force that acts on that is all again starting from the boundary layer theory. Well, I'll skip this now quickly to give you a general idea about application of this fluid mechanics. How many of you are related to engineering? Okay, so at least few are there. So now to give a quick example how this fluid mechanics is applicable to various engineering subjects or disciplines, I'll quickly tell you, let us say civil engineering. I'll not explain, I'll just show you the photographs. You will understand from there itself. So that itself shows you the applications in civil engineering. I'm just giving you samples. There are actually many. It's difficult to cover everything. Now let us quickly, somebody will be able to understand very nicely. This is a video which I possibly have taken from the internet. Now you see this. This is a very traditional old bowl with two idols. And now you can see that somebody is going to pour water in that. Okay. Now the water gets filled. Finally, what is the physics that you have to explain me? Observe the video. Furthermore, water is being poured. Okay, so there is small hole possibly somewhere, and that hole is getting filled. Okay, so now it is almost coming up to the brim, touching the feet of the statue. Okay, now the water started draining. Okay, so water started draining. Up to this point, it was not draining. The moment it touched some point, it started draining. And you see the bowl will be completely empty. So what is this mechanism or what is this process called? Anyone knows? Not exactly. Have you heard of siphonic action? So you go and check the siphonic action. So that siphonic action is the one that actually works there. Okay, and the same siphonic action is also used here. Okay, so the applications are quite large. There are a number of siphons which are also used in dams and reservoirs where you don't want overtopping of the flows. Now let us come to this. We are talking about wind energy. In terms of renewable energy, we are talking about wind energy. The application of this also is there. So you talk about bridges, large bridges. The stability of those bridges under strong wind conditions are also analyzed. So then you have saltwater intrusion and sea level rise effect. All that is studied here. Now let's quickly move. If I talk about mechanical engineering, you have all this. What is that? I forgot the combustion process. That also is going to be there. You talk about any mechanical lubrication and any system that is there. Talk about any vehicle, the streamlined bodies, the new designs that are coming up. So it's all based on the streamlining of the body and the fuel consumption that is going to happen. Aero, you have a lot of applications of that. I'm just showing one. Again, thousands and thousands of applications. Next, you come to chemical engineering. You have processes. You have different chemical mixings and reactions, all that. That also, again, fluid mechanics you need to understand. Biomedical engineering. This is again there, your heart pumping rate and all that is again based on fluid mechanics. You talk about your digestive systems. There also it is going to be applicable. These are kind of devices which is developed based on the basic fluid mechanics concepts. Okay, so nowadays people are also developing to measure blood sugar without piercing. So it is all, again, I'm not telling it's fluid mechanics. These are all technology which are being developed based on basic fundamental physics and science. Now, material science, again, there are a lot of applications, obviously. Your melting of metals and cutting of metals using water jets. You are seeing the apple being cut. Not only apples are being cut, the hard metals are also being cut using high pressure water jets. You can see this, the kind of metals that are being cut and all these designs, everything is being done. Then comes ocean engineering, which is obviously my region of interest or domain of interest. You talk about waves, tides, cyclones, storm surge, tsunamis, anything that you talk about. Anyway, it's all water, only different, density is different. So that we deal with. Tide in a day, you may see that it can go up to 5 floors high and 5 floors low at some locations. So these are various wave energy devices which are there in the ocean, and you need to understand the basic fundamental fluid mechanics concepts to analyze these things. Next, climate science, which is possibly interest to many of us. And there you talk about any global circulation, you talk about any kind of wind circulations, all that, atmospheric circulation, oceanic circulation, all that, again, fluid mechanics. So the overall basic fundamental idea of telling all these statements is understanding basic fluid mechanics properly is going to be useful. So if you have not done, then brush it up. All right, let us come to some of the topics on climate change and ocean dynamics. I'll talk about climate change impact on cyclones, storm surge, and coastal flooding. But before that, how many of you know what is cyclone? Okay, and how it is generated?
There's pure low pressure area, 25.
Low pressure area?
25.
Okay, so you are juggling everything around, but all are correct. So basically, if you have a high temperature region, then there is going to be low pressure region which will be generated. With this low pressure region, then you start with low pressure, depression, deep depression. All these are related to the pressure difference between the location and the ambient pressure around. So then the delta P is going to drive the whole cyclonic process. And then there will be a wind circulation. Then all the intensities we talk about, storms, cyclonic storm, or very severe cyclone, extremely severe cyclonic storm, super cyclonic storm, all that. So they are, again, based on the wind intensities, they are classified by IMD. So now the point what I'm trying to tell is, when you talk about cyclones, you basically talk about the pressure difference and the wind speed. Okay, these are the two major parameters we drive. But once the cyclone generates, the intensity is going to drive, or the intensity is going to decide what will be the extent of damage that's going to happen. So now how this damage happens? First of all, wind intensity is there, but what is the interaction between the ocean and the atmosphere? So ocean and atmosphere, you have wind stress that is acting on the ocean surface, and that leads to some kind of source generation or a push of the water mass, and that push of the water mass is going to propagate in a certain direction of the wind, and that will propagate towards some coast, and then that leads to the surge. And once the cyclone has a landfall, then the huge mass of water is going to flood towards the coast. So to understand all that, this understanding the cyclones are very, very important. If we look at the recent past, then this slide shows that our North Indian Ocean has quite less amount of cyclones, but even with that, it contributes to the majority of the fatalities or damage that happens, because we have highly populated region around the Indian Ocean rim. So given that aspect, if you look at Arabian Sea and Bay of Bengal, which is our domain of interest, recently in the last couple of decades, the intensity of the cyclones have increased substantially, and that is shown by power dissipative index, that is PDI. Okay, power dissipative index is calculated, and this PDI or power dissipative index is a function of the velocity or wind speed, you can say. Now, if the wind speed increases, the power dissipative index in cube terms. So a small increase in the wind speed is going to result in extensive increase or cubic term increase in the power dissipative index. So the damage is going to be extremely high. Now, the kind of damage you can see in some typical pictures, and this damage is going to be further amplified. Now, coming to the aspect that I wanted to talk about, the boundary as I discussed. So the wind is going to be, or wind stress or wind force is going to be transferred to the ocean surface. And when we are trying to model any numerical model, we are trying to generate the surge conditions. So what is the basic or what is the important aspect that we should look at? How good we are able to capture the wind energy, or we are able to transfer the wind energy from air to water. And once that energy transfer is proper, then next further processes can be followed. So this is one aspect which we looked at. And in this, you can see the drag coefficient, wind drag coefficient, which actually transfers the wind energy to water, is the major parameter. And that was defined by various formulations. You can see here there are number of formulations which are available. And this one initially which was proposed was increasing linearly, and then there is another formulation which is going up, and then it is cut off at certain wind speed. So why this was done? Initially people thought it is anyway with wind speed increase, the increase of drag coefficient is going to happen, but it was really not correct or true. So then slowly people realized that it will not increase infinitely. There has to be a cutoff at some point. So they did a cutoff for that. And this is Garrett's method, which is currently being used by INCOIS, Indian National Center for Ocean Information System, to predict the storm surge and give us the forecast. And if you look at, this is somewhere here, but these bars, what you see, is based on some measurements which was done by flying some aircrafts through the cyclones. And then it was observed that it is not increasing linearly, or there is not cutoff. It is actually increasing up to a certain extent and then reducing. So as the wind speed increases beyond certain point, the drag coefficient is reducing, the energy transfer is reducing, and that needs to be captured. So what we did, we developed this model, improved the model, wave boundary layer model we call. So with this wave boundary layer model, we tried to resolve all the processes that happens within the boundary layer. Your sea spray, your wave breaking. So in the ocean, there are hundreds of processes. We tried to capture all that and then did modeling of all the cyclonic events, all in the sense we considered different intensities of cyclones and different locations or different cyclones across the globe. And after modeling, we generated drag coefficients of almost the order of 100,000 data points. And with that, we created a kind of polynomial fit, and we found that this third order polynomial fit is fitting well with this, and that is now developed here. And this model we implemented in the numerical models that we are using to predict the storm surge. Okay, so the overall point what I'm trying to mention is the small gap that was present, which is basically the wind drag coefficient or wind energy transfer from atmospheric layer to the ocean layer. So that we try to improve. So similarly, tomorrow if you are going for some study, see such kind of points where you can possibly do some improvement so that it will be useful. And this formulation which we have done, still there are further scope for improvement. So now that was implemented in the formulations to calculate the storm surge, and we started calculating. Next, in terms of cyclones, we also try to understand the impact of cyclones if the cyclone approaches to a coast from different angles. So how the flooding is going to be there. So that is basically effect of coastal geometry and storm surge attack. So if you see here, if the cyclone comes from this direction, and this direction, where it is going to generate maximum surge. Now, why it is required? Because if you know the approach of the cyclone to a particular coast, and you know that it is going to create maximum surge, then accordingly, the preparedness can be there, and the flooding extent can be evaluated properly. So we evaluated that, and finally we found that around 75 degrees, if it approaches, it will be maximum. Then it is not only that, why it is maximum, that also was understood. If you look at a particular coast that was 75 degrees approach with a kind of concave coast, then the flux that is being pushed is not able to escape from the coast or from the area. So there is a kind of accumulation and push of the water mass towards the coast. So that basic physics or fundamental dynamics was also understood. Now, next, we also tried to understand the effect of cyclone intensification on storm surge. Now, we all hear that cyclone has intensified just 12 hours before or 24 hours before. Then once it is intensified, it may stay with that intensity for 24 hours or till the landfall, or it may stay for only 6 hours. Then again, it may reduce in its intensity. So what is the effect of that? And not only that, where it intensifies. If it intensifies in the deep sea, what is the impact? If it intensifies very close to the coast, what's its impact? So those things also we understood by doing an analysis and taking different intensification period and distance from the landfall, so that we can understand its impact. So these are various case scenarios we studied, and finally we arrived at the impacts with different intensities, and we concluded, or we found that if the intensification is somewhere between 6 to 12 hours, so that is mostly, the region is mostly within the shelf region, continental shelf region, then the impact is going to be maximum. So what we do, all these things, anything we do should be for the society. So finally what we do, we find out the kind of surge, or let us say the cyclone comes and impacts at some location, then what will be the extent of flooding? So that is what we calculate. So we tried to again extend it for climate change scenarios. Okay, so climate change scenarios, we know that there are now we are talking about SSP. So when we did this, we are talking about RCP. So we took 4.5 and 8.5 scenarios and tried to understand if there is a kind of intensification due to climate change and the wind speed is going to increase. Based on that, what will be the change in the flooding scenarios? So that also we evaluated and we found out for different reasons. So similar studies can be done and they can be given to various implementing agencies who can actually help us during such events. So with this, we also tried to work for a particular region along Odisha coast, where we tried to suggest suitable locations for cyclone shelters. So when the cyclone comes, people will be evacuated. Where will they go? They will be housed in some kind of cyclone shelters. And these cyclone shelters have to be constructed by government, but at which place? So there are a number of criteria. National Disaster Management Authority, NDMA, has given guidelines for finding out suitable locations. But in addition to that, they only give the criteria, but we have to find out the flooding levels. So flooding, based on flooding levels, we classify different zones. So this zone, what you call what you see as red color, we call it no shelter zone. So that is the initial 1.5 kilometer from any water body that is there. So there should not be anyone who should be present in those zones. They should be moved away from that zone. So out of that 1.5 kilometer, you have different zones, zone 1, zone 2, zone 3, classified based on various criteria and parameters of flooding. And then on top of that, we have to consider water body network. There is a river, there is a canal. So they will also be flooded during cyclones. So the road network going along that may be disconnected. So we have to consider all that. And then when you construct a cyclone shelter, the accessibility and reachability should be also considered. Then a cyclone shelter should be accommodating number of people. So per person square feet should also be considered, and then you finalize how many number of cyclone shelters are required. So based on that, finally, we gave number of cyclone shelters which needs to be constructed, and there are some cyclone shelters which were already present. Even if they are in the no shelter zone and they are already present, we don't want to obviously demolish them and remove it, throw it. So they can still be there. So we tried to analyze them also. And accounting all that, we created this kind of maps. So as a civil engineer, basic civil engineer, I don't stop at this place. We also did a design and gave the cyclone shelter that can be constructed. So we did it from the basic scientific analysis till the last mile. Okay. So next, coming to this another aspect that I want to talk about cyclones. So when there are cyclones, you have number of sensitive installations along the coast. You may have something. How many of you heard about the nuclear power plant that was flooded and the nuclear energy emission happened in Japan in 2011? That is called Tohoku tsunami. Okay. So because of that, there are a lot of damages and health problems. Everything happened. So similarly, there can be sensitive installations along the coast. Okay. And in such cases, there should be no flooding at all. So we did a study to find out a kind of protection mechanism where you should not have any overtopping of the storm water or tsunami, and that area should not be flooded. So for that, we worked on various profiles of the cross sections which were already there available by various researchers, and we found that they don't work. Then finally, we started working on that further, and we ended up getting a profile which actually gives us zero overtopping. That was suggested to the nuclear power body for implementation. So this is again considering you have to do a cyclone modeling, then tsunami modeling, then finally find out how this overtopping happens with a kind of sea wall, and then on top of that there is a crown wall. The crown wall profile will have different curved shape. So the basic physics what is involved here is in this profile, when the water comes or when the surge comes, it is first kind of pushed or rotated by the section which is below this point, and then that upper part is going to throw it back to the sea. So how efficiently that is designed, that decides whether there will be any overtopping or not. So that is what we worked on. So you first quickly push it or bend it, and then you have a large section which throws it. So different heights of waves will come. Your profile should be accounting or accommodating all the kind of waves that are going to come. Okay. This one. This one. You are talking about this width? These cross sections. Yeah, these are basically, this is a vertical wall. This is simple curved wall, but there is no forward bend. This is a curved section with forward bend. They are given in some literature earlier. There is something called Coastal Engineering Manual, international standard. They also have something. They have this one, circular and parabolic profile. But we tested all of that, but they did not, they worked for normal wave conditions, but they did not work for the surge and tsunami conditions. So for that, because the characteristic of the waves and the mass of water that is going to come is going to be completely different. So for that, when we started working, we finally ended up getting this forward backward 2 radius profile, which actually works. Okay. And because I was talking about this width, this depends on your civil engineering stability. What should be? You can reduce it at this point or this point, but that length is decided based on the stability of the structure that you need. Okay. So now this is something what I talked is the hard measure. Most of the times now you might have been hearing that along the coast you should not have any kind of hard structures because you are interfering with the natural processes. You need to have natural protection mechanisms. So for that, you either put sand or put some kind of plantations. So in those lines, we have also carried out some studies to understand how we can arrest or how we can resist the impact by putting some kind of natural vegetation. So for that, we did a study. There have been a lot of studies experimentally, but there are limitations with that. We also carried out a numerical modeling study, but numerical modeling study has maybe further more limitations. And our difficulty was how to model the debris with flexibility. You have a tree, you can put it as you can put a kind of rigid structure in the model, but putting a flexible structure in the model is quite complex. So introducing that flexibility was our challenge. So we used some kind of technique called SPH, smooth particle hydrodynamics for the fluid, and DEM, and for the vegetation model, we used SPH, DEM coupled modeling, and we did that. But when we did it, we could, now you can see the experiment we did, and with that, we also did a numerical study. The body is floating and going and hitting. So it is not only the vegetation, it is the floating debris. So when surge comes, it also brings a lot of debris along with that. It's not clear fluid. So technically in the laboratory and numerical models, we can study clear fluid, but simulating the debris, and it's not one debris, multiple debris with different shapes, sizes, and densities and all that, varying and simulating it is quite complex. So what we have done so far is only single debris, but the next step is somebody can do multiple debris and its impact. So we did that kind of study, and with that we also simulated the vegetation, where you have number of plantations, and if the debris comes and hits, how that affects the flow. And finally, when that flow passes across this vegetation, if you have structure, then how it impacts the structure and what will be the forces on the structure, how much reduction can happen, that is again studied. So this is one thing I can say is very starting point of this research. There are a number of aspects to this research one can do. So all those who are in mathematical background also can take up such kind of studies. All right. So now let me come to quickly to the waves part. How many of you have seen waves along in the sea? Okay, many. Can you define wave? Very simple. Can you define wave? Disturbance? In a medium. Okay, so we can have sound waves. Okay, we can have different types of wave. I am talking about, let us say, water waves, because I am talking about ocean. So now, in case of water waves, if I talk about a sinusoidal wave, what are the characteristics? Right? Something like this. This is, let us say, sinusoidal wave. So what are the characteristics of the waves that will have? Wave will have wavelength. What is wavelength? Distance between two consecutive crests or two consecutive troughs. Okay, so I can say from this point to this point, I have one wavelength. I define it as L, right? Then what else? It also has a height. So what is height? It is the vertical distance between the wave crest and wave trough. That is my wave height. And in addition to that, I'll have wave period. What is wave period? It is time taken for one complete wave to pass through a particular point, isn't it? Or time taken for two consecutive wave crests to pass across a point, or two consecutive wave troughs to pass across a point. That's it. Right? These are the basic characteristics of a very simple sinusoidal wave. But in ocean, what kind of waves do we see? Are they same every time? No. They are completely random. Their wave height varies from time to time. Their length varies from time to time. Their period varies from time to time. Okay. So most of the times, you see a random nature of wave in the ocean. So if you draw a time series, It could be completely random, right? Now, in most of the cases, if you want to go for design of design of anything, you cannot design for different wave heights. You need a single value. You want to design this building and you want to find out what is the force that is going to come. You tell me maximum, that's fine, but you cannot tell 100 values. So similarly, in this case, if I have to tell single value, what should I say? Maximum. If I say the maximum, then I might be overestimating. So we have something called significant wave height. Okay. So we define it as HS, significant wave height. Okay. How do we find it? We take a wave record. So I will have values H1 to Hn, n number of wave heights. Okay. So what I do, I take average of highest 1/3 of the wave heights. Okay. I don't know whether I'm writing it correct or not. So basically I'm taking highest 1/3 wave heights and then I take the average of that. Then the value that I will get is called significant wave height. All the mathematicians, you can correct me if I have written it wrong. Okay. All right. So this is how we find kind of a design parameter to be used. So in the real ocean, we have completely random waves. So when we try to calculate, we find such kind of parameters and then only we apply. So in this case, I'm now going to talk about the climate change impact on ocean waves. And then I will talk about coastal stability later. But when I'm talking about ocean waves, so this is how this significant wave height is the one that we usually compute and find out. Okay. So what we have done, we have taken the wind forcing from various climate models. How many climate model outputs are available? Let us talk about CMIP 5. CMIP 6 has come, but CMIP 5, if you take, how many climate models anyone is aware of? How many climate model outputs are available? Considering GCMs and RCMs, how many of you know GCM and RCM? Okay, not all. So what is GCM stands for? Global? And RCM? It's a global climate model, global circulation models, and regional. RCM is regional climate models, right? Okay. So I don't want you to be confused, but you have GCM, RCM, you can check for the names later. So if you look at, there are more than 77, or I think if I am correct, 77 model outputs are available considering GCM, RCMs. Now, which one I should consider? And there are statements that if you consider ensemble, then it is going to be better. But it is not necessarily always averaging everything is going to be giving you better result. Okay. So if you find out some best suitable models for the work that you are going to do, and then possibly if you take average of that, that might give you a better output. Okay. So what we have done here, we took some reference to a previous study where people told about 4 different GCMs and said that, okay, this model is going, these models are going to be good. They also talked about RCMs. We did not consider RCM. I'll tell you the reason behind that. So what we did, we considered those GCMs and we did the analysis. We found out the wave heights along these coastal locations. Okay. Just I'm presenting 9 locations here, just for a representation. We consider near term and future term, or near, you can say, sometimes people call it near future, far future. So up to 2041, we consider as near term. Then 2070 to 2100, we consider as far term. So that is what we considered. And we found that wave heights are increasing as we move in the future. And it is not only wave height, the wave direction. Waves are coming from certain directions, right? All of you know monsoon. What is the current monsoon direction? Which monsoon it is called? Southwest monsoon. Why? It is coming from the southwest direction. Similarly, waves are also having direction, and same way it is designated. So we found that the direction is changing. Based on the wind, you will have direction of waves. So when the wave direction changes, what are the implications of that? Does it really matter? It may not really matter to our normal general sense of tourism that we go to the coast. But practically to the coast, it matters a lot. The wave direction is going to affect the current that is going to take place along the coastal locations. And if the current is going to change, then all your sediment movement, the sand movement along the coast is going to change. We call it longshore sediment transport. And if that changes, then the locations which are facing erosion today, tomorrow it might be depositing. The location where it is depositing today, tomorrow it might be eroding, or anything may happen. So the coastal stability is going to change. Okay, so that is what we try to analyze. So how it is changing the wave characteristics, how it is changing the longshore sediment characteristics and the coastal profiles or coastal stability. So looking at that, we started analyzing the coastal stability. This plot shows the longshore sediment transport for different locations. And then based on that, the net sediment transport, net change in the longshore sediment transport we calculated. And then finally we calculated the stability maps. This is some stability map which has been generated by Central Water Commission based on the historical data, past data that they have accumulated. So in the similar lines, we have created the map for 2040 and 2070, how the stability is going to change. And this work we have done in a kind of larger scale with very coarse resolution. So currently there is another work which is just completed. We did it only for the Maharashtra coast. So having 2.5 grid spacing, or the resolution is 2.5 kilometers. So at every 2.5 kilometers, we can tell now what will be the scenario for erosion accretion or the stability of the coasts. So the application wise, it will have a lot of applications. That's what I wanted to highlight. I think I am overseeding the time. 5 minutes? Okay. So anyway, I have references that you can refer if you want. Now quickly, to give another important applications, that is basically extreme wave impacts on offshore coastal decks. So we have a lot of coastal structures, ports, harbors, jetties. So they will have some kind of open pile decks. So this kind of structures you will have. Now, if this kind of structures, we look for the future scenario, something that has already been constructed or that's going to be constructed. Now, if the wave heights are going to increase, their designs have to be accordingly done. And if, in addition to increase in the wave heights, we are also hearing about sea level rise. So if the sea level rise is going to be taken care, then what will happen? You have some kind of distance between the water surface and the deck. That distance or the air gap is going to be reduced. So if the existing structure I consider, the design was done for some wave height and the air gap was given for considering or not considering the sea level rise. Now in future, it is going to be impacted with higher wave heights, and because the air gap will be reduced, the waves are going to be impacting more frequently. So how do I consider that? So those analysis we did using a numerical model. So the kind of damages that you will see like this, if that happens, and it's going to cost hundreds and thousands of crores to the exchequer. So now quickly coming to the equation, I will not go through this. So this is a typical numerical model that we used called REEF 3D. And in that model, we have basic governing equations, that is RANS. RANS is Reynolds average Navier-Stokes equation. Same Navier-Stokes equation, but slightly modified. And in that we have time discretization. We have some scheme for capturing the free surface because you have air-water interface. Then finally we solve it using some kind of solver. Then finally we get the wave structure interaction. Okay. So by using this, what we did, we calculated the forces on the structures, and by varying different parameters, finally we had a kind of chord fit. So with that, we defined some kind of coefficients, horizontal force coefficient, vertical force coefficient. So once these force coefficients are obtained using wave height and air gap, S is nothing but your air gap, these two parameters, you can find out these force coefficients. Once you find out the force coefficients, you use that and multiply with this area or this expression. You have area here, horizontal projection area or vertical projection area. To find out vertical force, you use the horizontal projected area. To find out the horizontal force, you use the vertical projected area and find out the forces. That will be used for designs. Okay. So now the existing structures, if the force is going to be higher, then they will have to retrofit or kind of strengthen the structure so that it can take those loads and life can be increased. Similarly, we have done for different types of waves. There can be tsunami, there could be storm waves, there could be wave breaking on the structure. So all different types we did and developed such kind of formulations where it can be used by practical engineers. So eventually whatever we do, it should reach the last application stage. So then last one, quickly in 2 minutes, I'll try to highlight the evaluation of climate models' ability in simulating the near surface wind speed over the Indian Ocean, which is a study. In fact, that was my talk, which was initially scheduled, but I thought I'll give a broader overview of everything. So there, what we did, we took all these different climate models that are available and evaluated their performance. The performance we evaluated using something called relative score. So if you see here, we have something called total relative score, and that total relative score is calculated by the relative score of individual models and giving some weight to that. And those are calculated using some kind of assessment criteria statistic. If you see here, we have taken daily mean parking score, parking skill score, and annual cycle. It is basically significant statistical significance of the positive R that we have taken, and then significant statistical significance of bias. Mann-Kendall test we have done. So different tests we have done for different kind of trends which are suitable. And by taking this TRS was obtained for each model, and then we compared the models and found which models are giving or performing well. So finally, I will quickly show this slide where we found that these two models, let us say, are performing the best, or 2-3 models. Now, if we take the ensemble of those 3 models or 5 models, what will be the output? Instead of taking ensemble of all these models, which is not performing well. So then we found that by doing it, we are getting some good result by taking ensemble of the best performing models. So this is something done for CMIP 6 as well. So you can see here CMIP 6 models are evaluated, and there also we found not all, some specific models are performing well. So these results are published in this paper. One can refer from there, and we have given the models which are performing well for the land part and performing well for the ocean part. So depending on your application, you can possibly choose the suitable models to be used. Okay. So I'll not take more time. I'll quickly finish it. Okay, so yeah, again, this is another study which we have done for sea level rise. We have analyzed the sea level rise variability along the coast. We have global sea level rise given, but we can find out the regional sea level rise, and giving that input to the models, finding out the flooding is something that we have done. And by that, what we have done, we have found out the extent of flooding that is going to happen along different coastal locations that we have done for all along the Indian coast, and how much area will be flooded. Some sensitive zones might be flooded. What will be the extent of intertidal zone? So that all we have calculated, which have been submitted to the ministry for further use. So just to summarize that, let me thank the working group behind all this work, not me who has done all this. Thank you so much for patiently listening. And sorry for taking extra 10 minutes.
What is being celebrated? Manas, what is being celebrated?
That's my birthday. And the cake is not for me. That is for them.
have a question. Thank you for the amazing talk.
Sorry?
Thank you for the amazing talk.
Thank you.
I have a question on slide 50 or 51. I think it was one of these slides. You showed that you had classified the regions based on the amount of flooding.
Yes.
How did you calculate the amount of flooding in different regions? Was it through models or was it data driven?
This is the one, no?
Yeah, this slide.
We did a model study. That is basically you have, I don't know if I have something, possibly. Let me quickly see if I have. Okay, so this slide possibly will explain. So what we do, we create some kind of domain, generate some domain like this, and then the meshing is done. The meshing, you see here, the coarse mesh is in the deeper ocean, and along the coast you have finer mesh. And we do consider the topography part. We go up to all the way up to 15-meter contours. So assuming that the flooding is going to take place maximum up to 15 meter, which is not going to happen usually. So we take 15-meter contour, and up to that we do the discretization, or we consider our domain extent up to that. So this land area where we consider are the closer to the coastal locations, we use very fine resolution mesh, maybe 100 meter. Sometimes depending on the model stability, we may vary here and there. And that we do the modeling. So what happens when the surge comes and it also floods the land part. So there is a wetting drying scheme which is involved in the model. So certain portion may be wet, certain portion may be dry, depending on the flooding scenarios. So finally, with that, we find out the maximum extent of flooding. And then from there, we also find out the flood depths at different locations. So flood depths, what we do, we separate in every 1.5 meter approximately. So because 1.5 meter, the reason is we consider our standard normal height, which approximately you can see up to this. So one person can survive. So that we do a classifications like that, and then based on that we do a zonation. And based on the zonations, we have this depths as well and zoning. So priority is fixed. And when we actually design the structure, as I said, we also gave a structure. The structure has to be elevated to certain height. So that floor level, we call it flood level, we give it. So that level also we decide based on those things. Yes, we do it through modeling.
So you consider the topography of the land
Yes.
as well?
Yes.
Yeah, thank you.
Thank you so much.
Thank you for the talk. So I have question in the where you design a optimal shape.
I also forget sometimes where it is.
I think it was just before the flooding. 51 slide, 50th slide.
Yeah.
52nd, yeah. So do you use some shape optimization to get this curve?
Actually, it is shape optimization again has to be done based on some criteria. So what should be the criteria then? The point what we did is first we had these three shapes. So what we did, we understood the flow parameters. So when this flow is rising above that, how the velocity is and where the velocity vectors are changing its direction, and why if it is changing, then let us say the velocity vectors are coming up to this and then it is being pushed and it changes at certain point higher. So now if the velocity vector direction is changing at this point, but the curvature is changing at this point, then we play with that. So it is, we did not use any straightforward kind of mathematical formulation as such, but we tried to correlate the flow physics and the curvature point. Then we decided how it is happening, and then we gave a point, or we tried to slowly change maybe around 8 to 10 different shapes, and then finally we zeroed in on this. But I am sure that if we kind of develop some kind of shape optimization based on these parameters, we should be able to develop something. But we didn't do that.
We may get the same shape as your
possible, but as non-mathematician, I could not possibly do that. Okay. But it is possible to do that.
Thank you.
Yeah, thank you.
In this, you said that it was important for this structure to throw back the waves. So why is that throwing back necessary? Why can't we just let the waves go upwards?
Vertical direction.
Huh.
So if the wave goes in the vertical direction, somewhere it has to fall, no?
But like I'm imagining that throwing back requires like more rigidity of the structure because
Well, what happens? It is not only one wave. There will be number of waves, one after other. It will keep coming. So if you don't throw back, then the next wave is going to come and reach behind that. So eventually there will be overtopping to the other side. Now, if I say this is my wall, so if I keep pushing some water, and if I don't throw back into the sea, then what will happen? It will be on the air, right? When it splashes, it will again splash to this side, which is not desirable. So the overtopping should be completely nullified.
I was just imagining that throwing back requires more momentum change as opposed to.
That's true, but somewhere the mass has to be taken care where this mass will go. It cannot go to the air. It cannot
It
stay
will
there.
fall back, but then
Where it
we
will
are
fall
not
back?
doing that.
Where it will fall back? It will fall back in the same place. Then what will happen? There is another mass coming. So if they crash, then what will happen? There will be overtopping. That is what happens in this. That is what happens. This will possibly straight away throw up. But again, when it falls down, the next wave comes, eventually it overtops.
Okay. What was that approach angle? You showed 75 degrees.
Okay, so that was when the cyclone comes. Usually, let me go to that. Yeah. So when a cyclone comes, this is coming. So this is my coast. Okay, I'm taking from this side of this coast from towards that is mostly towards the north. So this is my 0. So from 0, if I take, this is 45 degree, this angle, this is 75, this is 90 degree. So that is what is my approach angle. And most of the cyclones that are in the northern Indian Ocean, they are anticyclonic. So if we see, the cyclone is going to move like this. So if it is moving like this, the wind on the right side is going to push the water towards the coast, whereas wind on the left side is going to pull the water away from the coast. So most of the times what we see, on the right side of the cyclone, the surge is going to be maximum. On the left side, it is slightly less. So now if this angle is 75 degree, what happens when it is pushing? So this is the area where it will keep on pushing, and the area available for the water to escape is going to be very, very less. So that is why the maximum flooding takes place. So that is what something the basic flow physics or flux dynamics was analyzed.
Thanks.
Thank you.
Okay, so we'll take one last question that's in chat. In the chat, if you look at the chat,
Okay.
you should be able to see this question.
I'm not able to
Maybe
that. Yeah. Would it be useful to give some curvature concave to the wall doing the throwback? Concave. Yeah, it is. I'm not sure because the curvature is already concave. So I really didn't get a clear understanding of the question. Already the curvature is given and concave shape is given. So only the point of curvature or the change point, that was the measure parameter. And yes, we have given 2 radius. So we have tried with different curvatures of both the radius that are assigned. And with that, finally, we ended up with this. But one thing that I do agree, that kind of mathematical approach to figure out the shape optimization is going to be useful. Okay, picture looked like it was flat, but I don't think it was flat. Let me come back to that picture again. Yeah, so this, yeah, from afar off it looks flat, but actually if you look at this one, this curvature, where it is. I don't have a pointer here, so I'll go
The
to full
chat
screen.
box.
I think this online mode.
Yeah, he'll move the chat box. Yeah, this is good.
Yeah. So this curvature, if we see, this is not flat. So there is one radius here, one curve, and then the second curve starts. So there are two radiuses, and this curvature actually meets. Yeah. Thank you. So yeah, they are actually cleared now.
Yeah. Okay.
Thank
All
you.
right. Thanks. Let's thank Manas again, and we'll break for coffee.
Thank you so much.